Hello, today I will be doing a presentation from Chapter 2 and it's Project 1 on Pascal, Fernat, and Méré. So I have set up an outline here with some points to talk about. The first one will be biographies of these three men and also other things that they contributed to math. We'll look at the question that was asked by Méré and the letter exchange between Pascal and Fernat, and then a complete solution for this problem. You will also notice that for each person, I decided to just throw in a quote that they said. For Blaise Pascal, the one that I enjoyed the most was, "The more I see of mankind, the more I prefer my dog." All right, the first person that I will be talking about is Blaise Pascal. He was a French mathematician and a physicist. He was born on June 19th in 1623 in France and passed away at 39 on August 19th, 1662 in Paris. Pascal was born to a mathematician. His mother died when he was just 3 years old, and his father never remarried, so a maid was appointed to take care of him and the other children. But his father was very devoted to his children, and he educated them himself and encouraged them a lot. Pascal proved to be a child prodigy. His father was impressed with Pascal's fascination with math and would take him to meetings at the Mathematics Academy in Paris. And at 16, Pascal presented some of his early theorems, including his mystical hexagon, to an audience which included great mathematical thinkers of the time. Pascal also created the syringe and a hydraulic press. He invented these in the 1640s. The hydraulic press is an instrument based upon the principle that became known as Pascal's law. He also worked on the mathematical theory of probabilities, which is what this whole slideshow is about, when he worked with Fernat on this. And then the last thing is Pensées' work. Pascal had a very religious experience in 1654, and he was writing letters that attacked casuistry, which was a popular ethical method used by Catholic thinkers. And in later years of his life, he was of very delicate health, hence why he died so young. And so he was working on an apology on Christianity, but it was not completed before his death. And this apology was a collection of fragments written by Pascal, which represented Pascal's defense of the Christian religion. Pascal did have some other math contributions. The first one is the mystic hexagon, which I did mention just earlier. Pascal discovered that if a hexagon A, B, C, D, E, F is inscribed in a conic section, the points of intersection RST of the pairs of opposite chords are collinear, and you can generate the conic through points A, B, C, D, E, since F can be derived from an arbitrary line AX through A. Moving X and F traces the conic. Move A, B, C, D, or E to get a new conic that passes through them. And yes, that is a lot of words and letters. The next is Pascal's calculator. He started working on the calculator in 1642 after watching his father perform exhausting calculations and recalculations of taxes. The calculator was also called Pascalin's, which he continued to improve by 1645, but they were not commercially successful due to their high cost. The device could add and subtract two numbers directly and was capable to multiply and divide by repetition. Pascal's law states that pressure applied to a confined liquid is transmitted undiminished through the liquid in all directions, regardless of the area to which the pressure is applied. So that relates back to the hydraulic press. And finally, excuse my French, trait du triangle arithmétique was published in 1653. It describes a convenient tabular representation for binomial coefficients, and it is now called Pascal's triangle. Second quote in the slideshow, and perhaps posterity will thank me for having shown that the ancients did not know everything. And this is from Pierre de Fermat. Pierre de Fermat was a French mathematician and a lawyer. He was born August 17th, 1601 in France and passed at the age of 63 on January 12, 1665. Little is known on his early life, so it was hard to find some facts, but his college education was at College de Nevers in Montauban. He worked on the restoration of Apollonie de Loci Planis, again French. And this happened when he moved to Bordeaux and began his work in mathematics. He performed the restoration and also produced significant work on maxima and minima. He served in local parliament. In 1631, Fernat bought the office of a council in Toulouse and held that office for the rest of his life, where he was a lawyer. And finally, mathematical theory of probabilities is again what this slideshow is about, and that was worked on with Pascal. So, like Pascal, Fermat had many contributions also to math. The first one was he developed add quality, which is a method to find the maxima, minima, and tangents to curves. And he also discovered a way to find the center of gravity in different plane and solid figures. Next up is the analytic geometry and optics. This work was published in Descartes' famous La Géométrie in 1637. Fermat's Little theorem was first mentioned in a letter to a friend in 1640, and the theorem states that if P is a prime and if A is any integer, then A to P is equal to A or mod P. In particular, if P does not divide A, then A is to P minus 1 equals 1 mod P. And so here we have mods just like we did in chapter 5. And finally, Fermat's last theorem, also known as Fermat's conjecture, was stated in Arithmetica around 1637. He wrote the theorem in the book's margin and added that the proof was too big to fit, and for 358 years mathematicians struggled to obtain the proof, but in 1994 his theorem was proved, and according to the theorem, no three positive integers, a, b, and c, satisfy the equation a to n plus b to n equals c to n for any integer value of n greater than 2. The last quote of this slide presentation is, "Nothing is more precious than time, and that is what we think about the least." And this comes from Chevalier de Méré. Chevalier de Méré was a French writer, an amateur mathematician, and a gambler, born in 1607, and he passed on December 29th, 1684. Born Antoine Gombe, that was his original name, but as a nobleman, he adopted the title of knight for the character of his dialogues representing his own ideas. And then he used Méré because this is where he received his education. He was a salon theorist, so like many liberals, he was suspicious of hereditary power and democracy, and believed that problem solving through free discussion between minded, educated, and worldly people was preferable. The Honest Man and True Honesty were his best known essays, though he was far better known for his contribution to the probability theory. So, how exactly did Méré contribute to the probability theorem? Known as Desmarais' problem, is a question posed in the mid-17th century to Pascal and marked the birth of the probability theory. One of Méré's favorite bets as a gambler was that at least 1 6 would appear during a total of 4 rolls of die. And so he asked Pascal if he would be able to figure out why this was, or why he had this thought. Here, before I give some more information on the whole letter exchange between Pascal and Fernat, I wanted to show you just a picture here. This is supposedly one of the letters, and at the bottom, this one is signed by Fernat, so it was to Pascal. So when Pascal was given this problem, he realized that he would need to invent a new method of analysis to solve this puzzle, and since the solution would need to reflect each player's chances of victory given the score at the time that the game was interrupted. Thus began the correspondence with Fernat over the course of several weeks, and it laid the foundation for the modern probability theory. Their respective methods involved listing all the probabilities and then determining the proportion of time that each player would win in order to solve this question. Fermat and Pascal each had their own approach. Fermat's approach rested on a complete enumeration of the possible outcomes. For example, if the winner of a coin toss needs to win the best of 5 toss and one player is ahead 2-1 when the game is interrupted, there would have been 4 possible outcomes had the game continued, and 3 of those 4 favor the player with the edge. Ergo, he should win 3/4 of the pot. Pascal's approach, devised an algorithm employing what is now known as induction and incursion. It involves a logical cycle of playing out each possible outcome for each successive round, starting from the point where the game was interrupted. And when the end state is reached, it is possible to work backward through the intermediate steps, assigning a number to the probability of winning for each player. So Fermat and So we have finally made it to the complete solution. And Méré, as I mentioned before, he was a gambler, so he was fond of a dice game in which he would bet that a 6 would appear at least once in 4 throws of a die. And how it's written here is different from how we did look at it in class. And so for this first part, he wins with at least 1 6, and it takes more time to figure out how to get at least 1 6 because it could be 1, 2, 3, or 4 6s, so it's easier to find the probability of getting 0 6s, and then subtract this from 1 to get the probability of him winning. And so to get no 6s, we count. There are 4 rolls, and each of the rolls can be any number besides 6. So there are 5 choices, as that's why the number 5 is on top. Total ways to not get any 6s, and the sample space is any way to roll a die 4 times, which is 6 to the 4th, so the 6 is on the bottom. And again, this is the losing probability, so the winning probability would be this 1 minus 5 or 6 times 5 continued equals 1 minus what it equals, 0.48 equals 0.52 chance of winning. So after this, Méré then decided to introduce a new game played with 2 dice and bet that at least 1 double 6 would appear in 24 throws of 2 die. And so he thought he would do just as well as before, but he actually lost more often than he won. And so Pascal and Fernat then produced an explanation for him. So you're rolling a pair of die 24 times and trying to get at least 1 pair of 6s, and there are 36 ways to roll a pair of die. And so one of those ways gives a pair of 6s and the other 35 do not. So if we rolled the die and didn't want any pair of 6s, we would count 35 to the 24th power ways to do that. And the total number of ways to roll a die is 36 to the 24th power. So the probability of getting no pairs of 6s is 35 to the 24th divided by 36 to the 24th. And this in turn means that the probability of getting at least 1 pair of 6s is 1 minus 35 to the 24th divided by 36 to the 24th, which equals 1 minus 0.51, and so it's a 0.49% chance that he will win. And finally, this last page is just my sources. I used Blaise Pascal biography, Pierre de Fermat biography, Antoine Gombard, who is Méré on Wikipedia, and Desmarais' problem. Thank you for watching.